Okay, this is the wave equation. What do we do with it? What kind of waves do we get? The easiest type of wave to talk about, and the kind that we're going to spend the rest of this chapter and really most of the rest of the semester on, is the plane wave. Let's start from the idea of the Laplacian. So the Laplacian of E is equal to the second derivative with respect to each of the coordinates, all added together, of E. And these get applied individually to each of the vector components of E. So if I write this all the way out, it's very long, you get partial x squared EX plus partial y squared EX plus partial z squared EX, and the same thing for y and z. And now the z component. This is what I get for trying to write this on a Friday. All right, that looks right. So each of those second derivatives gets applied to each of the vector components of E. So we're doing all of that. And this is still a vector. So that's the x hat component. That's the y component. And that's the z component. Now we're good. This, the Laplacian has different representations in different coordinate systems that lends itself to expressing different waves most easily. And in Cartesian coordinates, the easiest wave to deal with is a uniform plane wave. A uniform plane wave has phase fronts that are planar. So you can always define a plane that is a surface of constant phase for this field. What this looks like in practice is, let me give you an example. A plane wave electric field could be given by some amplitude times some polarization vector times e to the minus j k, and then some expression of direction. So here we're going to have it be propagating in the plus z direction. Now, if we want to know where are the surfaces of constant phase of this thing, where are the phase fronts? Those are any plane of constant z. So choose some value for z, plug that in. That is a surface of constant phase, because this electric field doesn't have any position dependence. That's just some amplitude. It can be complex, but it doesn't depend on position. That's what a uniform plane wave is. The the only position dependence is along the direction of propagation. So, as the phase progresses, as that e to the minus jkz term loops around the unit circle, you are moving forward towards positive z. Let's do a quick example about this. So now let's do a quick example about uniform plane waves. First, we're going to verify that the thing we think is a plane wave, that a plane wave is a solution to Maxwell's equations, or to the wave equation. To start with, let's remind ourselves of what the wave equation actually is. So that is that the Laplacian of E is equal to start with, let's remind ourselves of what the wave equation actually is, and that is that the Laplacian of E plus k squared E. I'm assuming a lossless medium for now, so the wave number k is omega square root of mu epsilon. We'll talk about lossy media next time. That is equal to 0. So let's find out if that's actually true. If we are going to do the Laplacian of some amplitude times x hat e to the minus j kz, find out if that plus k squared times the same thing equals 0, question mark? Well, let's find out. This Laplacian, if you remember, does second derivatives along each of the Cartesian directions. So there's no x derivative, no x dependence, no y dependence, because this is an x hat vector, but it doesn't depend on, it doesn't change as you move along the x-axis. It's still x-directed. But there is z dependence. So then what we got to do is second derivative with respect to z of e naught x hat e to the minus j kz plus k squared e naught x hat e to the minus j kz. Is that equal to 0? When we do this second derivative, we do the first derivative, you get a minus jk. You do the second derivative, you get a minus jk e to the minus jkz. And this vector component and the amplitude stay the same out in front. So minus jk times minus jk turns into minus k squared. So the whole thing works out to be minus k squared e naught x hat e to the minus jkz plus k squared e naught x hat, wrong e to the minus jkz. That does in fact equal 0. So yes, that is a solution to the wave equation. Plane waves are real waves.